Our first speaker is, I think everyone have heard of, and is Professor Konstantin Novoselov, and from University of Manchester. And I'm sure everyone knows that Konstantin and Andrew Gain won the Nobel Prize in 2010 in physics. And I don't think I need to introduce more than that. And but I do want to tell you that this is Konstantin's first trip to Australia, and we're really delighted and privileged to have him give his first talk in Australia and at this conference. And today, Konstantin Novoselov will give a pleasure talk on one of our heterostructures. And please join me to welcome Konstantin.
Good morning, everybody. It's a great pleasure to be here. And first of all, I'd like to thank the organizers, especially Michael and Antonio, for giving me this opportunity to give a talk at this very nice conference. Also for pulling together a very nice program as well, for arranging fantastic weather and good sea, at least on Mancunian standards, and for the Chardonnay yesterday as well. So let me start with a story, and I should apologize to those who've seen this picture before and who've seen this story before. It's probably my last chance to tell it, because we just, since a couple of weeks ago, we got a new director for the National Graphene Institute. Volodya Palko just moved over to Manchester, and he's leading this institute. That's how it looks now. It's pretty much operational. That's how it looked just 1 or 2 years ago when we were doing an archaeological survey. And so during the survey we discovered, you could guess that there is probably not that much history in Manchester to dig. So we discovered rows of 1780, 1820 terrace houses, but also the remains of fairly large building, which has been identified as an Albert Clubhouse. Now, the reason people remember about this Albert Clubhouse is because this gentleman was the member. It was the club for German expats in Manchester during the Industrial Revolution, and this is Engels, and he was the member of this club. Now, every single building on the university premise is supposed to be named after a famous Mancunian. Like physics is Schuster Building, math is Alan Turing Building. So we immediately, or at least I immediately thought that it would be really nice to call the National Graphene Institute the Engels Building. Now, when I passed this idea through our governments, the reaction, quite predictable, stupid me, was that we give you money to do research, not to explore a communist past. So it didn't exactly work out. I waited until the general election last May. It didn't work out either. So we still haven't got the name for the building. We're still searching. But the morale here is that same as the Communist Manifesto hasn't been written by one person alone. We're not going to concentrate only on graphene in this building. It's the whole structure of all the other materials which we are going to study in this National Graphene Institute. Now, of course, there has been quite a big progress over the last several years in terms of mass production of graphene. We don't need to go into the Scotch tape method anymore. Depending on the price and the quality you want to achieve, you can use many different other methods how to produce graphene, from liquid phase exfoliation to CVD to epitaxial growth and molecular assembly as well. Now, the interesting part is that this mechanical exfoliation is, of course, still being used quite a lot, and you can start thinking about exfoliating not only the lead pencil, but also all the other pencils as well. And then if you do it you will basically get into many other two-dimensional crystals. And of course, the exciting part is that many of them are coming very stable. Those which are not stable, we know how to stabilize them. And very often, the properties of those two-dimensional crystals will be very much different from the properties of their three-dimensional counterparts. And this gives us quite a unique opportunity, and let me just give you let me put it a little bit into a perspective. If you think about it, there are only so many materials which determine our world, like electronics, it's all silicon, for example, and then all the other examples. And we learn to live with this, but of course it creates lots of limitation on what we can do, because one material means only one set of parameters. If an engineer wants to create a new device, he would have to first consider what silicon can do for me, and then create a new device which follows the parameters of this material. Alternatively, of course, would be nice to have composite materials or heterostructures where you combine different materials and the properties of different materials together. And of course, there are some examples of those materials, but those examples are still few and far between. So ideally, we would like to have it more versatile, to have some more versatile methods how to produce new heterostructures. And really what you want is to be able to create those heterostructures from scratch, by atom, or at least layer by layer engineering. Then you can, say, assign certain functionalities to pretty much every layer of atoms and create some functional materials out of that. Now, because we have lots of two-dimensional crystals which collectively cover a huge range of parameters, what you can do now, you can try to pull them together and arrange them into quite complex heterostructures, and say so this is not just random assembly of those materials. It's actually quite functional. So the top 6 would be a tunneling transistor, and then the next few, like 5, would be a solar cell, for example. And that's exactly what I would like to talk about today. Is about the progress which we are making in creating those heterostructures. But maybe a few words first on the quality of the materials which we can do. So some time ago we tested the quality of our heterostructures. You basically take one of the devices. It was from Leonid Ponomarenko. It's the device for drug experiments, and you sacrifice this device, basically cutting a small part out of it, pulling it out, something like that, and looking at it in TEM, and you can see all those 2D crystals quite well. You see boron nitride, graphene, and so on. And here is another example of a heterostructure like this obtained by similar method. You basically here we started with boron nitride and then added 2 layers of graphene and then 2 layers of boron nitride, more bilayer graphene, bilayer BN again, and then more bilayer graphene. It was for tunneling experiments. But interestingly, if you look at least in the dark field image, you won't be able to say where your boron nitride stops and where graphene starts. So it's really, if you do it carefully, the quality of those heterostructures become extremely high. Now, since some time ago, what we started to realize that it's not only important which materials do you put together, but also how do you put them together. Because of course, a part of the degree of freedom that you can choose whichever materials you want, you can also, when you assemble them together, you can misalign them according to your will. And here is one example of 2 graphene layers, which we try to, sorry for a bit of the psychedelic picture, but it's basically, it was meant to represent two graphene layers which can be misaligned and rotated when you put on top of each other. The interesting part would be that if you misalign them in the real space, in the reciprocal space, they will be misaligned as well, and your conical dispersions would be either close to each other for the top and the bottom graphene, or they could be separated by quite a large. They could be separated in momentum space. And if you make those devices like this, it's quite an easy device to make. You basically take two layers of graphene, separate them by thin boron nitride, 2-3 layers of boron nitride, and you align them to a certain degree, maybe 1 or 2 degrees alignment. Then your IV characteristics of such a tunneling transistor. I mean, it's probably one of the simplest device you can make, and it works as a tunneling transistor. Its characteristics become quite interesting and quite unusual. So your current increases with increase of the bias voltage, but at a certain moment it reaches a peak and then it goes down. Generally, it's called negative differential conductivity or negative differential resistance, if you want. And it's quite an important effect because if you have this negative differential conductivity, you can have your device basically acts as an amplifier, and you can have high frequency oscillations in such devices. You can basically plot the same curves for different gate voltages, which so you can gate them, and then you have this diagram. What is important for us here is that everywhere you see this blue area is the area of the negative differential conductivity. So it's di over dB, and then blue is negative. It's quite. Now, I first, just to show you how similar picture would look for non-aligned devices, which you completely misalign the two graphene, and it looks very much different. As you can see, there are no negative differential conductivity at all here. But you see some other effects, like those lines, for example. It's the effect of when the Fermi level goes through the Dirac point, because the density of state is 0, the dIdV, the conductivity is 0 as well, and those vertical lines is phonon-assisted tunneling when the bias voltage equals exactly to one of the phonon energy, and then you can emit a phonon and conserve momentum still. But it's just to highlight that there are quite a few effects going on simultaneously in those tunneling structures. Now, coming back to this negative differential conductivity, it's quite a simple way how to understand where is it coming from. So if you think about those two cones, if you want to satisfy momentum and energy conservation, those two conditions are satisfied only if you have the Fermi level crossing one of those crossing parabolas where the two cones crossing. So here the Fermi levels are just those points, so the current is 0. Now, if you apply small bias, your Fermi level is quite small, the current, and it's not touching this cross section, the current is still 0. And then once your Fermi level reaches this parabola, this cross section, your current start to flow, because you can satisfy both momentum and energy conservation conditions. The interesting part comes when those two cones overlap along this line, and all those states can tunnel with momentum and energy conservation, and you have this peak in the current, and then you get out of this. And and you get the number of states which satisfy those conditions decreases, and then you have a decrease in the current. So it basically, all you need to know is is to remember your from your school math or geometry lessons, the conical cross sections. The trick is that those conical cross sections, you need to remember not only about momentum conservation and energy conservation, you also have to think about the chirality conservation as well. And so it's chiral conical cross section. So something which they don't teach exactly in school. That's how it looks. Those cross sections would look like if you think about chirality as well. But at the basis of it are still all the conical cross sections. Now, can we see experimentally this chirality effect? Because so far all this effect is just geometrical. There is nothing. There is not much of the specificity of graphene at all. Can we see the chirality effect in this in these tunnel experiments? Well, the answer is yes, we can. And to do that, what we need to do is to apply magnetic field parallel to the layers perpendicular to the current. And if you do this, you apply Lorentz force, of course, on your electrons, which tunnel. So they basically they start to bend like this red arrow. And if they bend, it basically is the same as shifting all the states in the brilliant zone by a certain vector. So you started with this picture, you applied magnetic field, and your blue hexagon is now shifted and it becomes the green hexagon. And you can see if my cones were overlapping here, they stop overlapping here. So it means that my resonance would shift either in gating or in gate voltage or in bias voltage. Now, what you also notice that all those 6 cones, 1, 2, 3, 4, 5, 6, they have now different conditions for this overlapping. And rather than 1 peak, which I had before, I now have got 6 peaks, and those 6 peaks basically correspond to the 6 corners of the brilliant zone. Now, basically measuring, sitting at each of those peaks, I can select the particular electrons, not only from a particular valley, but actually from the particular corner of the brilliant zone as well. And I can selectively say that I want those electrons to tunnel, and I can sit at this peak, and they would tunnel there. And so now what I'm going to do, I'm going to rotate magnetic field, and in reciprocal space, it means that one of my layers in reciprocal space also moves like this. If I do that, that's what I observed for the position of the peaks. It should be 6 peaks. You don't particularly notice them. There are 2 reasons for that. One is it's in experiments it's a little bit of the blurring, but also only half of the peaks are visible. And the reason why only half of the peaks are visible is because of the chirality conservation, which I told you before. So that's the simulation, and you see that all the lines which go, so it's basically sinusoidal, 6 sinusoidal peaks which we just intervene all together. But what you can see that on those sinusoidal, all these lines are much brighter than those lines, and that's exactly what we see here. You only see those lines. You don't see those lines at all, and that's exactly because of the chirality conservation. Well, conservation is probably the wrong way to say it. what we do, we project your electron from graphene onto the vacuum state in boron nitride, and it's the projection of the two-component wave function into one component, and then you project it again on the two-component in another graphene. But so you can say that it is conservation. But basically, it's as close as you can possibly get to seeing the chirality in the transport experiments. The only other experiments I know where you can see chirality clearly are the ARPIS experiments. That's probably the as close as you can get to the chirality observation in transport. And also, what you can do now, you can sit at this particular peak and say that I want particular electrons with particular chirality and particular corner from the particular corner of the brilliant zone to be available in my experiments, and you basically create valley polarized states by tunneling from a specific valley. Now, one of the application is that you want to try to use those resonant tunneling devices for the real applications. It's been those devices were available since 70s, maybe before in gallium arsenide, and the reason why they're not widely used is because those devices do not operate well at room temperature. Graphene doesn't care; it's low temperature, room temperature. It's this NDR peak, this negative differential conductivity is still there, so it works quite well. So you can actually put it into a real circuit, and it would make this circuit to oscillate. So it is operational, and our estimates show that you should be able to get into hundreds of gigahertz frequency quite easily. Now the next, so those results on this chirality, we've been obtaining them for maybe the last half a year or so. Something which came only a couple of weeks ago. We tried to do the same for monolayer to bilayer tunneling, and apparently you can pull the same trick as well. The picture is much more complex, because now you have to think about not only tunneling between the two cones, but also tunneling into the two subbands from monolayer to two subbands in the bilayer. So that's why there are quite a few of those lines, and only narrow areas where DIDV goes negative. But still there are quite an extended areas where it goes negative because of the good nesting between the high energy bands in bilayer and in the monolayer. But if you do the same trick with the rotation of the magnetic field, again you see those sinusoidal which are going only in one direction, and it's actually you see it much better than in monolayer. There's the simulation. It doesn't exactly fit with the position of the resonant, and we're still guessing why in bilayer it's much more difficult to get a good fit. But at least the idea that because of the chirality you have only half of the states contributing to tunneling, you can see it extremely well in this monolayer to bilayer tunneling, and this is the results which we have obtained in high magnetic field just a couple of weeks ago. So let me now switch gears a little bit and go to a bit more complex heterostructures. What happens if you shine light on this tunneling transistor? Well, in principle, what would happen that you should be able to photoexcite electron hole whole pairs. The problem is if you don't have any built-in electric field, it will just immediately recombine. Another problem is if you use boron nitride, of course you have to shine 6 EV or so lights, which doesn't exactly help at all. Well, it's quite easy to solve both issues. You can apply, say, gate, for example, and built-in electric field. So now if you shine some light, photoexcite electrons, then electron would go into one contact, hole would go into another one, and you would get the photocurrent. And the problem with the boron nitride, you just replace it with, say, with one of the transition metal dichalcogenides, and then it's this band gap is reduced to 1.7, 1.9 EV or so. So the structure again is very, very simple, same as I showed you before. 2 layers of graphene separated by a couple of layers, 1, 2, 3, 4 layers of transition metal dichalcogenide. That's how it usually look like. There are lots of sacrificial layers here, but the most important are the bottom graphene, the tungsten disulfide in this case, and the top graphene. And then if we shine light across it, you would see that the photocurrent you would measure only if your light shines exactly in the area where all the 3 layers overlap. The good thing is about transition metal dichalcogenides is that the huge density of states, which this is the calculation done by Antonio and his co-workers, and because of this huge density of state, the quantum efficiency which you can gain from this are quite high. Even our simple non-optimized devices could give you 30% of the quantum efficiency quite easily. Now, what you can do, the question which you can ask is, what happened? Can you reverse the process? And rather than shining light at those heterostructures, can you actually try to emit light? So, can you inject both electrons and holes into this barrier or semiconductor and try to gain something out of this? Well, the question is, in principle, yes, and then you will be able to emit light. The problem is that the lifetime of those of the electron and hole in such a structure would be extremely short. Those electrons and hole would disappear into contacts very, very easily. The coupling time into an exciton is extremely long, and the exciton lifetime is quite long. So those electron and hole would disappear into the opposite contacts, and they won't contribute at all to the light emission. Unfortunately, because of that, you have to do quite a bit more complex devices, something like this, where the transition metal dichalcogenide would be now separated by boron nitride barriers from graphene. And basically the reason why we have those barriers is to increase the lifetime, the dwell time of our electron hole pairs inside of this quantum well of transition metal dichalcogenide. So now you inject electron hole pair, they are allowed to create an exciton, and the lifetime, which is controlled by the height and of those barriers and the width of those barriers, is if this lifetime is large enough, then this electron hole pair is allowed to recombine and eventually emit light. So that's basically the simplest device which you need to make for such a structure, for an LED structure, and typically we would call those transition metal dichalcogenide quantum well, because our electron hole pair would reside there for quite a long time. The band alignment between graphene, boron nitride, and transition metal isocyanates, of course, depend on the material, but it's pretty much always possible to find the right parameters in terms of bias and the gate, so to get efficient injection and efficient light emission as well. The unfortunate situation that you have this band gap in transition metal isocyanates, it's not exactly aligned with the Dirac point of graphene, and especially most often it would happen that the Dirac point would be pinned by some defect states in transition metal isocyanates. So first you would inject electrons, most typically, and then you would inject holes. So first you would have some current flow and no emission at all, and then you would, when you inject both electrons and holes, you would get some photo emission. So that's the photoluminescence for molybdenum sulfide. So that's the neutral is the neutral exciton peak. Those are the impurity states at certain moment. Once you start injecting electrons, you have the charged exciton peak as well. No photoluminescence yet, and then once you inject both electrons and holes at quite high bias voltages, you start to get some electroluminescence out of those structures. Now the good thing is that it does work quite well. So you can apply voltage and you emit light, and you just about see it with your naked eye. It's about 1.7, 1.9 EV. Well, at room temperature it's a bit lower. So, but you can see those. You still see these lights reasonably well in the microscope, and the question is how to improve the light emission from those heterostructures. Well, I should say that even this relatively simple heterostructure would give you about 1% of the quantum efficiency, which is in principle a good start. But still, we need to figure out how we can improve the quantum efficiency of such heterostructures. Well, one way how you can do it. So why the quantum efficiency is low is because still those electrons they escape through those barriers. What you can do is try to catch those electrons and into another quantum well next to your original one, and you basically come with the idea of multiple quantum wells. Of course, it's a bit of a laugh on my behalf towards my students, but they have to create those heterostructures, and you understand that we do it layer by layer mechanically, so it's all done by hand. It's quite a job, but I would say these days a heterostructure with say 4 or 5 quantum wells takes them maybe 4 or 5 days to make. And but the beauty of those that pretty much every single one of them does work, emit light this way or another. So it takes time, but the yield is almost 100%. And then you can vary different parameters. You can vary the thickness of those boron nitride barriers. So if you do the same TEM trick, you would see mostly transition metal isocyanates, because the tungsten and moly and molybdenum is so much heavier than boron or carbon. You pretty much don't see the boron nitride or graphene. So your tungsten or molybdenum is much brighter in TEM. So now, if you do that, you would see lots of steps in this in the IV characteristics, which probably correspond to voltage dropping across each of those quantum wells. And then your photo emission, your electroluminescence become much stronger. So you can get up to 10% for quantum efficiency in for quantum well devices. Now, what we found recently that not all the materials are the same. So we started with molybdenum as sulfide and tungsten as sulfide, and it worked well, but the quantum efficiency for pure layer was about 1%. Now, recently we tried tungsten. Sorry, it's not the sulfide. It's tungsten diselenide. I should apologize. And if you try tungsten diselenide, the structure of the emission is much richer. And to be honest, we are still debating, and there is still debate in the literature which line belongs to which. The X naught at 1.72 eV is pretty much settled. That is the neutral exciton. X minus probably correct. Then what are those states? We still don't know. But the beauty of tungsten diselenide is that its quantum efficiency, even for one single layer, can be 10%. So if you put several quantum wells, you should easily go above 50%, and then maybe close to 80, 90. The real interesting part for tungsten diselenide is that quantum efficiency increases with increasing temperature. Pretty much all the LEDs which you find which industry uses, the quantum efficiency goes down with increasing temperature. Even worse, typically the quantum efficiency would go down with the driving current. In our case, the quantum efficiency increases with the driving current, which is again something which we don't completely understand at this moment of time. Most probably, it is related to the fact that the ground state for tungsten diselenide is predicted to be the dark exciton because of fairly large spin orbit splitting in the conductance band. However, tungsten disulfide is predicted to have similar structure, and yet tungsten disulfide doesn't give you the same quantum efficiency, and it doesn't increase that much with temperature. So we're still puzzled why tungsten diselenide works so much better for PR and EL. So now, before I finish, just a couple of more notes on how you can possibly increase the quantum efficiency. One is a simple way. Unfortunately, you cannot make thicker layer. You cannot put a thicker layer here for the quantum well, because your transition metal dichrocargonite become indirect band gap, and you don't get much of the photoluminescence. What we tried is we tried to put turbostratic transition metal dichrocargonites. Of course, it has been shown that even turbostratic transition metal dichrocargonites would become indirect, which is understandable. You have strong, even if it is turbostratic, you've got strong interaction between the bands at the gamma point. So, and then you have a deep in the gamma point for the conductance band. But yet, for some reason, if you have turbostratic device and then you apply sufficiently high bias voltage, you get a very good electroluminescence at the direct band gap, which again something very puzzling and something which we don't understand at this moment of time. And the final note is that I showed you all those heterostructures, which are 3, 4, 5 quantum wells. But yet, even though we've got 5 quantum wells, it's still maybe 20 layers of different materials. So 20 layers would be still quite transparent, so it can, and very flexible as well. So it can form the basis for flexible and transparent electronics. So just I'll put my conclusions, but before that, I would like to thank all my collaborators now. So The resonant tunneling work is mainly done by Artyom, and Freddie have done most of the LED work here. Thank you so much.